All right, we are on to some examples where the projectile is not just launched horizontally, but rather at some angle above the horizon. So let's take a look. Example 4, projectile is going at 200 meters per second, 60 degrees from horizon. So let's take a look. We've got our object, and it is being fired. That's not quite 60, but we'll pretend like it is 60 degrees and 200. There you go. Same questions apply. You know, where, like, how far is it gonna be, like, when it lands? How far away does it land? That kind of thing. But this very first example, it does ask us a few sub questions. So, question A, it just says, it's basically it's asking for the vertical and horizontal components. So back to, and I've brought this up in this unit, but when we did vectors and we tried to do applications of vectors and we said, you know, a soccer ball kicked at 30 degrees going 20 miles an hour, we were asked to find the horizontal and vertical components of that vector. So that's what question A is really just asking. So we have 200 meters per second at 60 degrees. So how much of that is in the x direction and how much of that vector is made in the y direction? So all we're doing is just saying 200 times cosine 60. And that is for the x and for the y. So if you need help or if you don't remember how we figured out the x and y components of an angled vector, please come see me. That's not for this lesson, so I'm just going to keep moving on. So if we look at this, 200 cosine of 60, cool. Cosine 60, excuse me, is 100 because cosine 60 is a half, and therefore half of 200 is 100. And here we have 200 sine 60. Well, sine 60 is square root 3 over 2. The answer ends up being 100 square root of 3. And just to let you know how I get that, it's 200 times square root 3 over 2. So if I look at this 200 times square root 3 over 2, it's really, we can break it down and say 200 times the 1/2, or 200 divided by 2. That's where we get the 100, and the square root 3 just stays there. So we've answered A. B, I guess the x and the y, box that in. So then B says, how long is the projectile in the air? That is exactly like the other problems we've done. We just have an extra component for x and y. So if we look at the traditional, x is equal to 200 cosine 60 times t. See, now we don't just say 200t because it's not cosine of 0. We're not shooting horizontally. So our x component is still 200 times cosine of the angle times t. We just have to have 60 in there instead of 0. Then we have y is 200 sine. So there's our velocity component vertically. We have our gravity component. Now, it does not specify this particularly. It just says projectiles fired at 60 degrees with a horizontal. It doesn't say how far off the ground. It doesn't specify whether it's on the ground. So in those cases, if you don't have a piece of information that says the projectile has an initial height of this or of that, we just assume that it's 0. So h naught, h sub 0 is 0. So you're going to use that same method where we set y equal to 0 to find how much time passes while the object is in the air. So we have 200 sine 60 t. Well, we've at least got it down to one equation, one unknown. 1.9 t. Here we can divide by t, and we get 4. We already decided that 200 sine of 60, 200 sine 60, that's really just 100 square roots of 3. I'm going to convert that. Nope, sorry, I left that t in there. We divided by t on both sides, so that goes away. So if we take 100 square root 3 divided by 4.9, it is in the air for t equals 35.35 seconds. So the sub-question of part B, how long is it in the air? 35, about 35 and a third. Let's see, part C. Part C, we're going to take, it says, what's the horizontal distance? Well, just like the other problems, we're going to take x equals 200 cosine 60 times t. So really x is just equal to 100 times t. T was 35.35. So x is 3,535. And that is my answer. Horizontal distance traveled 3,535 meters. Let's see. Yeah. Let's do this one quick. I think. Let me check something real quick. I think we have time to do this one here. So I paused it just to look into and set up this problem in the calculator for us. But anyways, let's do example 5 very quickly. Same problem, same type of problem where we have an angled velocity. There we go. So except this time, cat is jumping at 40 degrees. So our vector looks like this. And meter and a half off the ground at 40 degrees, 3 meters per second. Not very fast. Is how far out from the piano does cat strike? So this one here, actually, we do get to just determine the horizontal velocity or horizontal position. So let's do this. We say x is equal to our initial velocity times cosine 40 times t, and y is okay. Here's where this one is different. This one here has an initial height, not 0. So because we have this term, see in the previous example 4, we didn't have this constant term. We were able to just simply move one of the t terms over, divide by t, and then solve for t. Here we can't. We actually have t squared, t, and a constant. So we have two options. We can either um, go and do the good old quadratic formula and say x is equal to negative b. Everyone remembers this. B squared minus 4ac all over 2a. There we go. So we can use this formula. We can say a is negative 4, b is whatever 3 sine 40 is, and c is 1.5. And then we would only use the positive term. Or we can graph this, which is what I would recommend. So this is where, to save time, I actually already created the equations in here. So I typed it in, 3 cosine 40 and t, and then the y equation. When it came to the window, this cat's only jumping from 1.5 meters, so I didn't imagine it would take very long. So I only evaluated for 3 seconds. If we need to extend it, we can. In the X distance, how far away did I think she landed? Probably not more than 5 meters, because she's only 1.5 meters off the ground. Same thing in the Y direction. Now the Y direction, I know that she jumped from 1.5 meters, so my 2 might be a little short, but you can pause the video and look at these window settings, but I'm going to hit graph. And there's our cat. She jumps from 1.5 meters and then lands less than 2 meters away. So the best way to do this can be just tracing. There's 0.7, 0.8 is way down below. So I can go second graph to get my table. And I can see that, nope, I need to go second window. I'm way off my mark there. I was around 0.7. That's where I want to start my table. And sure, 0.01 looks great. So there's my 0.7, 71, 72, 73. So what I'm looking for is for my height in the Y table to be 0 or change from positive to negative. So here we are from 0.78 to 0.79. That's roughly where it is. If you just use that as your estimate, you would say that X is about 0.78 meters from piano. And that's good enough. So, yeah, there's a couple of things different about this one, but if you end up with an angled vector so that your y has a t term and a t squared term, and you have it not launched from the ground, you either have to do quadratic formula, or what I would prefer is just use your graphing calculator and the table to get an answer nearest to the nearest hundredth of a unit, in this case meters. So that is it. I will probably get some videos for the practice problems as well, but that is it for the lesson.